Is there any way I could ask a question about last class?
Sure. You can ask me now. I'm ready.
Could you just give another example of the not logic?
Yeah, that was a little hard to think about. I'll do that, and I'll tell you the best way to think about it until we get into the actual programming language that you need to do to implement that. So let's do this. Let's go through, and I want to just kind of briefly touch on what we talked about in the last class, and then I'll answer that question about not logic, and then we'll get into the new stuff I want to talk about today.
Okay.
Before I do that, two things I want to tell you about. Number one, I was thinking about quiz number one, and I think what I'm going to do, because at the end of the last class, I kind of rushed through the topic of relays, and that's actually pretty important to understanding logic and how PLCs used to work. So I think what I'm going to do for the first quiz, instead of giving it to you on Friday, I'm going to make it go live on Friday, and you'll have the whole weekend to do it. But what I'm going to do, I found a really nice video on relays. It's not that long, but the guy in the video does an excellent job of talking about and explaining what relays are, how they work, and different types of relays. So I think what I'm going to have you do for the first quiz is watch that video, and I'll just have some basic questions I ask about, and I'll say more about it on Friday. But I'll send that out the next day or two. I'll send the link out. And then the second thing, I don't know if I have anybody that wasn't here that missed the last class, but if you go to the class website, the homepage, at the very bottom of the list of topics, you'll see a link. It either says past lectures or past videos. I can't remember. But if you click on that, it'll take you to the video that you missed. If you missed the last class, please make sure you review that. We want to take these things in order, and I think things will make sense if you do that. So if you ever miss a class, you can go there. I try to update that a day or two after I've recorded the video, and I'll probably get behind on it as things get more busy at school, but we'll see. I'll do the best that I can. So let's get into this. So in the last class, we talked about a lot of stuff. It was kind of an introduction. One of the main things you want to understand is the difference between a switch, a button, and a sensor. And then we talked about the difference between those three devices, and then we talked about types of switches, and we talked about states of buttons. So let's kind of just run through that quickly. A switch can be open or closed. A symbol for a switch, a basic switch, a simple switch, is like this. So that represents a switch that's open, and I can draw the same switch closed. I gave you kind of an anatomy of the switch. This thing right here is called a pole, P-O-L-E. And the thing that the pole touches when you close the switch, when you move the lever, when you turn the light on, you make the pole and contact come together, and then you have a circuit, a complete circuit through which current can flow. So this represents an open switch, and this represents a closed switch. And one of the things you got to be able to do is name the switch. What type of switch do I have? Well, you can name a switch by the number of poles it has and the number of ways you can move the poles to close the switch. The number of ways the actual pole can touch a contact. So for example, here I have a single pole, one pole, and I can only move it one way so it can touch a contact. The way you can move it, the number of ways you can move it is called the throw. I'm saying throw like you throw a baseball. So this would be, if I name this would be a single pole, single throw switch. You would ask for an SPST device or switch. And so in the first video, if you missed that, go through and we practiced that just a little bit. You should be kind of familiar with that. We talked about buttons. A button, unlike a switch, the switch has that throw. You can throw it in the on position. You can throw it in the off position. When a button, you push a button. And we kind of know what these devices are. You've turned the light on and off, so you've dealt with switches. You pressed the doorbell, or you've opened the door in your car or the refrigerator. You've noticed the button there. That button can be pressed. But the state of the button is what's important. I can have a button. With the button, you have two contacts, and the pole is kind of horizontal like that. And then you got this piece that you can press on. And so I can have it like that, or I can have it like this, and in both cases there's a spring. That spring puts force on the pole. In this case, that spring is forcing that pole up like this. So if I want to close the switch, I got to press the spring down. And so if I don't touch it, the pole and the contacts are separated, and so the switch will be open, and we will call this a normally open. The idea of a device being normally open or normally closed is really important in this class. So a normally open push button, and the normal state of the device is the state of the device. If you lay it on the table, you back up from it, no human interaction at all. If the contacts are open, we have a normally open device. If the contacts are closed, we have a normally closed device. In this case right here, I have the same setup, but this time the pole was on the bottom of the contacts, and the spring is pushing up on that pole, keeping the pole and the contacts together. So the normal state of this button is to be closed, so we call this a normally closed push button. So you want to make sure you understand types of switches: single pole, single throw, double throw, that type of thing. You have to name a switch. Button can be normally open, like a doorbell. Button can be normally closed, like the button you see on the refrigerator door. When you open it up, it turns the light on. So you want to make sure you're clear on that. But here's the thing: we can take those switches, we can take those buttons, and we can connect them up in different ways so that we can make decisions. We can have an electrical circuit make decisions for us, and that's where this stuff kind of gets cool. Because now I can automate processes, and I don't have to be there. I can make things happen by using what we call simple AND logic, OR logic, and NOT logic. So I want to just kind of touch on that real quick. Let's go back here though. Sensors. What's a sensor? Well, a sensor is a transducer. A transducer is any device that takes energy in one form and converts it to another form. Now, what we're going to do in this class is we have this computer. We're going to talk about specifically what this thing is. But for now, it's called a PLC, a programmable logic controller. Just think of it as a heavy-duty computer. And what we want to do is we want to take these physical quantities outside of the computer. Anything outside of that computer, we call that the field. Anything outside of the PLC is called the field. So we deal with things outside the PLC, but what's inside of that computer, what's inside of the PLC are signals, different types of signals that I want to talk about. So sometimes we can take like a button, or we can take a switch, and we can hook it up in a way that we can feed a signal into that PLC directly. But sometimes we have other kind of information we want to get into that computer or PLC, and I have to do something to it. So I want to talk about those different types of signals. But a sensor takes in a special kind of a signal that we'll talk about here in a second, and it converts it to some other kind of signal. So for example, I can take temperature and convert it to an electrical signal. Now, by electrical signal, I mean a voltage or current. Either way you want to think of it is okay. So I can take a physical quantity like temperature, and I can convert that to a voltage. So maybe if the temperature goes up, the voltage goes up by a certain amount. There's a certain transfer function or relationship or rule that relates how the quantities increase or decrease. There's a certain rule that describes that. So I can have something that changes a temperature to a voltage, or maybe a pressure to a current. And then we can feed that inside the machine, and we can do stuff with that we'll talk about here shortly. So when you're dealing with that kind of stuff, let's see, I kind of lost my place. Then we talked about relays. This is kind of where I slipped up. I let the time get away from me. The thing about it is when you have these switches, I can hook a switch up in a certain way to where I have AND logic. Let's talk about that AND logic real quick. So if I have switches hooked up, and if you had the circuits course, you'll recognize this as a series circuit. So if I have a switch here, and some device here. Let's say I have a motor right here. That's a motor, and I got some kind of power supply right here, and this is switch A and this is switch B. What we said in the last class, if they're connected up like this, if they're connected up in series, the only way to get that motor to run is both switches have to close. If switch A is closed and switch B is closed, then I have a complete path through which current can flow and that motor will run. If I open up either switch A or B, it won't run. And so in the last class, we talked about the definition, the name of that. This kind of logic is called AND logic. AND. With AND logic, the only way to get a true output, the only way to get something to come on is for all the conditions to be true or all the switches to be closed. So AND logic. And then we said, okay, well, what if we do it like this? What if instead of hooking those switches in series, what about hook them in parallel? If you had the circuits course, you'll recognize this as a parallel circuit. And you can see from the picture, it's pretty easy to see. I mean, it's not rocket science. If this is A and that's B, now I have two paths for current. If I close switch A and I leave B open, current can go this way and the motor will run. If I open A and close B, current will go this way. Or if I close both of those, now I have two paths. The only time the motor won't run in this condition is both of these are open. And so with OR logic, anytime I have a true input, anytime I have a switch that's closed, then I'm going to have an output. The only time I don't have an output is if all the inputs are open or false. And so I showed you the truth table for that, the definition. Now somebody asked about NOT. That's a little confusing. It's kind of hard to describe, but here's the way I want you to think about NOT. The way I want you to think about NOT is this. Let's say you have the same circuit and a motor. What I'm going to use for the input is I'm not going to use a switch. I'm going to use a normally open push button. Normally open push button. So it looks like this. Then I got my motor. Now what I can do is I can make a table of inputs and outputs. So maybe I have my inputs and my output. Now we'll say the button, let me just say button. The input is a button, so I'm going to call this button. The button here can be not pressed or it can be pressed. So the button can either be not pressed, it can be in this normally open state, or I can press it. Well, if this button is not pressed, then I don't have an output over here. The motor is off. I'm going to say that this is false. If the button is pressed, then this is true. Now, typically what we do, we don't use this switch. We'll do it like that. We'll use a normally closed button. And then we'll use the logic values like this. Here I have to reverse it now by using a normally closed button. If the button is not pressed, then you see we have an output here. If it's pressed, it's in this state. And this will turn it off. So the truth value determines, how do I want to say, the truth value for the NOT function depends on if the button is pressed or not pressed. And so we'll use this normally closed push button. And if it's not pressed, we'll say that that's false. And if it's pressed, we'll say that's true. Now, I never think I do a good job of explaining the NOT function, but here's the thing. Here's what the NOT does. And it'll make more sense later in the course. Because we're dealing with switches now, guys, but what we really deal with is little piece of information in the computer called a bit. I'll probably talk about bits today. And the important thing to understand about the NOT function is not so much how it behaves here. This is good because this is the way we used to do it. But what really is important about this is what these functions and or and not what they do to the bits. And if you don't know what a bit is, we'll talk about it. But what you really got to understand about NOT is whatever the state of the input is, the NOT function will change it to the opposite. That's what's important. So I don't know if I did a good job of explaining it with this, but I think when we get to the actual use of this, with bits and bytes and all that. It'll be crystal clear. It's pretty simple. So I don't know who asked it. Was that AJ? Who asked me that question? I don't know who that was, but just roll with
it made sense with the normally closed button, because when you use the normally open, it just looked a little like AND logic, but with only one thing. But it makes sense with when it's closed.
And that's the way we'll think about it with the normally closed button. So who is that talking? Is that AJ?
No, it's Will Pascal.
Okay. Guys, I'm trying to learn. I don't think this is going to work because my memory's not that well. I'm getting old and forgetful, and then I can't see your faces, and I like to know my students. So I'll try to do the best I can. Okay, so let's get into this now. So we have a situation where I can make decisions. Now there's basically, so far, there's three kinds of decisions that we can make. I can make an and decision, I can make an or decision, and I can make a not decision. What does it mean to make an and decision? Well, what that means is the only way to get an output with the and type of logic is all the inputs have to be true. For now, think about all the switches have to be closed. So if I need that kind of functionality, I will use an and circuit, and logic. And I gave the example in the last class. If you get in your car and you stick your key in the ignition and the door is open at the same time, there's a switch. Switch A is in the ignition, and you close it with your key when you stick your key into the ignition. So switch A is closed. When you open the door, there's a normally closed push button on the door seal, and when you open the door, that switch closes, and now that second switch is closed. If they're hooked up to give us and logic, now I can have something happen. The thing I have happen is the buzzer that you hear when you're sitting there with your key in the ignition, the door open, you hear the buzzer going out. That's an example of and logic. So if I want that kind of logic, I would use this. Or logic means I just need one event or the other event to happen, or both events to happen in order to have an output, a machine turn on, or whatever you want. In the not logic, what we do is if I have a situation where I need to reverse something. So I have something true, but I need for something else to be false, or vice versa, then that's the candidate for not logic. Now, how do sensors come into this? Well, we'll actually kind of get to that, but sometimes I'll have, well, let me just get into the meat of the conversation, and then I can talk about sensors. But before I do that, relays are important because what relays allow us to do, instead of having an actual circuit that I have to manually go in there and turn this switch on and turn this switch off, what I really would like to happen is for my electronics to handle all of that automatically. And so I think of a relay as it's an electromechanical switch. I can hook this to a computer or some other device, and instead of me turning the switches off and on, I can have that device turn switches off and on to control something. So I don't know, I have an example of a control circuit that when we meet face to face, actually hand that out and you look at it and try to go through it, and you can see the and logic and not logic. I may put that up on Canvas so you can see it. I usually make that your first quiz, but when we do this online stuff, that's a little hard to do. So let's get into what I want to talk about today. So these terms, you're what I call digital babies. You grew up in the digital age. When you think of the term, you've heard of the term analog and digital. And I'm going to ask you guys, when you think of analog, what do you think about? And there's no right or wrong answer. All I'm asking is, when you see that, the term analog, what does it mean to you? What does it make come to mind? What do you think about? Can anybody answer that?
Something
What do
like
you think about? Go ahead.
manual. Something that's manual.
Okay, manual. Anybody else?
Like physically pushing a button or turning a switch.
Okay. All right. Anybody else?
I would say mechanical.
Mechanical. Okay. Those are good thinking. What about digital? Anything come to mind when you think of digital?
Coding. Sometimes it can be done through a code.
Ooh, okay. I like that. Actually, yeah. Go ahead. Anybody else?
A system that basically runs on itself, more or less.
All right. So I wanted you guys to kind kind of throw that out there, what you think about when you see the term analog or digital. And when we use those two terms in this class, we mean some very, very specific things. We mean something very specific. So I want you to make sure you're writing this down and that you follow me. And please, if at any point if I'm not clear or you're confused, please ask me and I'll go back. So I want to be crystal clear with this part. The first thing to understand is this. Those switches, buttons, and sensors that we talked about, what they're controlling is something called a signal, an electrical signal. Now, when I say signal, what is a signal? Well, a signal is a voltage or current. And I'm not going to go into what a voltage is or what a current is, but everybody's familiar with voltage because you deal with batteries. You know, a car battery is 12 volts. One of the little D batteries or cells is 1.5 volts. You pretty much know what current is. You might call it electricity or juice, but you kind of have an idea. What we deal with are these signals. And so I have these signals that I can channel into a computer using a switch, a button, or a sensor. And that signal is going to be of a certain type. So that signal either is going to be of an analog type or a digital type. So I'm going to use the term analog or digital, but what I really mean is analog signal or digital signal, okay? Because I'm looking at it as what it's going to look like inside the machine that we're talking about, the computer. So for analog, here's what I want you to remember. What we mean by analog is continuous. It means the signal is continuous. And what we mean by digital is discrete. The signal is discrete or it's broken up into pieces. So analog means continuous, digital means discrete or in pieces. An analog signal is a continuous signal. A digital signal is one that's broken up into pieces. So I'm going to pause for a second, write that down. Analog means continuous, digital means discrete. Now, most signals, or let's not say signals, quantities. Let's deal with physical quantities. Physical quantities. Let me think here. In nature, do you think most physical quantities are analog or digital? Like, I don't want to lead your thinking, but are most things that we measure, you think they're analog or do you think they're digital?
Digital.
Digital, okay.
You say when you're measuring something?
Yeah, most physical quantities that we would measure, like, what do you think, what's the most measured quantity in the universe? Well, can't say in the universe. What's the most measured quantity on the planet? Anybody, just take a guess. What do you think the most measured quantity on the planet is?
You mean what is taken the most, or like what is the most?
What is the most measured quantity? The most measured quantity.
Money?
A good one.
Yeah.
I was gonna guess mass maybe.
Time.
Mass, another good one. I heard it.
Time.
Say it again? Time is the most measured quantity. Time. And even though the clock, listen, even though the clock ticks, maybe from 1 second to the next second, and it looks like it's in pieces, time is really smooth and continuous. The next most measured quantity on the planet is temperature. Now, when you wake up in the morning, and let's say it's 32 degrees outside, and you get up in the afternoon and you look, and now it's 50 degrees outside, it doesn't jump up from 32 directly to 50. It doesn't go from 32 degrees to 33 degrees to 30. It goes from 32 up in a continuous kind of way. And so it turns out that if you think about physical quantities we can measure, like time, temperature, force, acceleration, all those things you talked about in physics, if you want to make measurements of it, even though you might take discrete points and make a graph, they're really continuous. The point I'm making is this, is when we talk about this device called the PLC, if I want to measure some physical quantity outside of the PLC, more than likely that physical quantity, not all the time, but most of the time, is going to be analog. Now, that's a problem because the PLC I want to stop saying that. I want to talk about the computer. Because really the other part of this class that we're talking about are computers. Now, the computer we're talking about is a special type of computer designed to control industrial processes, but all it is a computer. The thing is, computers cannot work off of this. Computers only understand this right here, which we'll define here in a second. So if I have a physical quantity, like temperature or time, and I want to put that into a computer, well, I got to do something because I cannot inject analog signals directly into the computer. Let's move to this one. Digital means discrete. It's broken up into pieces. Now, often there's situations that I can use to represent. Think of it like this: either something's there or not there. Anything that you can represent to be in one state or another is a digital quantity. It's broken up into pieces. An example would be like you can have a light. A light can be on, a light can be off. So I can represent that with a voltage that represents the device being on, a voltage that represents the device being off. Anything that you can break up into pieces that's not continuous is what we mean by digital. Now let me back up for a second because I want to go back to something. Let's talk about this.
Did we lose him?
I was about to ask, did his
Yeah, we fucking.
thing
Yeah,
get
I
cut?
think we lost him.
I think
Oh, does he not know? Oh shit.
There's no way he knows.
Text.
He probably won't know.
He's
I would say
reconnecting.
text him, but the text comes from his computer.
I
He's
would say
reconnecting.
send him a message.
Hold up. No, I'm giving the man a call. Hold up.
Ah,
Google
no,
text
you can't call him.
Go back.
Oh, there it is.
Oh shit. Wait.
He's-
Wait.
we lost
We're
him.
losing you, Professor.
Wait. We got you. I think we got you.
Yeah, we lost you there for like a minute.
Oh, what? Am I back?
Yeah, now you're
Yeah.
back.
Yeah, your stream cut out for a minute.
What part did I drop out on? Do you
Right
remember?
before you wrote. I think right before you wrote computer. It broke
Okay, all right. So let me go back to this. So I want to talk about a computer. What is a computer? And I asked the question, what is a computer? And a computer is any device that contains a special circuit or special device called a microprocessor. So here's what I don't want you to think. I don't want you to think that a computer is just a laptop. I don't want you to think that a computer is just your desktop, the thing that you have on your desk. A computer is anything that contains a microprocessor. And guess what? Your laptop contains a microprocessor. Your desktop contains a microprocessor, but so does your cell phone. Your cell phone contains a microprocessor, therefore your cell phone is a computer. You may have a programmable microwave, or on the wall in your living room or dining room, you may have a programmable thermostat. Even though you're calling it a microwave or a thermostat, it contains a microprocessor, therefore it is a computer. So I want you, for the purposes of this class, to think about computers in a different way. A computer is any device that contains a microprocessor, and the only thing or the only type of signal that the microprocessor understands is this type. And so that's why an understanding of these two terms is important. Now, I want to give you another example. Now, I don't know if you guys know what a Polaroid is, a Polaroid picture, but I'm way older than you guys. So back, I remember as a kid, my mom brought a camera called a Polaroid camera. And it was kind of cool because you can take a picture.
I think we're about to lose him again.
Yeah, UC's internet isn't the best sometimes. I think he's streaming from there.
Streaming from home?
No, I think he's at UC right now on campus.
Oh.
Yeah, that internet isn't the best.
Unless he has a large whiteboard at his house.
Well, we're screwed.
Then for some reason, I want to I want to print this picture either on the web or maybe I want to put it in the magazine or newspaper. So I give this to the Inquirer, and they're going to run this on the first page of the newspaper. So the picture that they put in the newspaper looks exactly like the one that I gave them, except that, has anybody ever looked at a picture really, really close in the newspaper or in a magazine? If you look at a picture really, really close on any kind of print medium, even on your computer screen, although you won't see it, if you look at it like under a magnifying glass, what would you see? What would you see?
Pixel.
Isn't it like a bunch of ones and zeros?
Okay, you will see a bunch of ones and zeros, but not really ones and zeros. What you would really see are dots. You will see dots. Now make sure, I want to be clear here. If I looked at a Polaroid picture, the colors and the lines, they kind of mesh together in a continuous way. If I took and made a copy of that same picture and I put it in a magazine or in a newspaper, and I took a magnifying glass and looked at it, what looks like a line is really, if I look at it under a high enough magnification, is really a bunch of dots like that. And each one of these dots is called a pixel. It's called a pixel. So the point I'm making is this. The picture I take with the Polaroid camera is analog, because the information that makes up the images and the colors, they're continuous and they mesh together in a continuous way. If I take that same picture and I make a copy of it to put in the newspaper, and then I look at that picture under a magnifying glass, I see that lines that look continuous are really a series of dots if I make the magnification strong enough. You've probably already seen this before. Matter of fact, when you buy a computer screen or you buy a flat panel TV, if you're into the technical part of it, one of the things that separates one device from another is how many pixels they use to represent the image that you will see. So a pixel is just a little tiny single piece of information. But here's the point I'm making, is that in the analog world, things are continuous. If I want to get that into a computer, like that flat panel TV I just talked about is really a computer. Why? Because it has a microprocessor in it. So if I want to get information into it or out of it, it's got to be digital. So we'll take this and we'll turn it into something like this. Now you might say, well, that's kind of interesting. How can we get away with that? Well, the thing about it is this, is that if I have information, if I have digital information, and if I have it close enough together like this, I don't know if you can see it in the camera, but I can actually have these pieces of information so close together that it looks continuous. That's kind of how I can get away with that. But I'm not done yet with defining digital, because there's a little bit more to it than that. So let me back up a little bit and go through another example, because digital is a little bit more complicated. This is not a digital signal. I don't mean to imply that. This one right here, you can see it. That is an analog representation. Anytime I have a continuous signal, it's analog. But this is not a digital signal. This is not what I mean by digital. I want to be real clear here. Let me go and give you another example. Let's say we're going to measure, let's say we're going to measure, again, if you have your mic open, mute your mic. Somebody has your mic open. AJ, I think it's you. I got a mic next to you. Are you there?
No, mine I can mute on its own, so it's been off the whole time.
Okay. Well, guys, mute your mics, and then if you have a question or you want to make a comment, you can unmute it. Because what happens is, I think this thing picks up, it switches over to you guys when you hear background noise, it switches away from me. But let me get back to this. So let me think. Let's say you want to measure. Okay, let's do the example I said before. Let's say you're going to measure temperature. So I got temperature, and this is time. So the temperature here is, let's say it's in degrees Fahrenheit, and the time here, let's say the time here is in hours. So let's use this example. So you're gonna start right here, and we'll start at 12 a.m. So it's 12 o'clock at night, right? And we're gonna measure the temperature. And so what I'm gonna do is I'm gonna mark off these hours. So your job, I give you the job, and I say, all right, student, here's what I want you to do. I want you to wake up every hour, and I want you to record the temperature. So let's say when you go to bed, maybe, I don't know, maybe the temperature is right here. No, let me make it lower. Maybe it's right here. Say the temperature is right there. And then you get up every hour, and you take a reading. You end up with something like that. So there are your data points. And then, of course, if you make a graph out of this, that graph is going to look like this. Even though you took the temperature at certain discrete times, you know it didn't go from whatever this temperature is to this temperature. It didn't jump from here to here. It actually went up in a continuous way. That's why I said earlier that a lot of, not a lot, but most physical quantities that we measure are continuous. Temperature is continuous. I go from one temperature to another, not by jumping over, but by continuously increasing or decreasing in value. So here is my graph, and it's an analog graph, but if I want to make this a digital system or digital graph, here's what I have to do. What I'm actually going to do is take each one of these data points here. Here's a data point right here. And I'm going to give that a value. Now, somebody mentioned, when I asked for a definition of digital, somebody mentioned zeros and ones. And what's this idea of zeros and ones? Well, it turns out that if you go back to the definition I gave you in the beginning of the lecture, I said digital means discrete. Anything you can represent using one value or another. For example, a motor can be running or not running. A light can be off or on. Something can be there or not there. Anything you can represent it being in one state or another, then we call that's digital thinking. And so what we do is we do this. We use signals, we use voltage signals, and I'm going to just use an arbitrary number here. If something is, say a light bulb is off. If a light bulb, we're talking about a light bulb, it can be off. I'm saying, all right, well, if it's off, I'm going to say that it's false. If that light bulb or motor is on, I'm going to say that that's true. So now I can use this idea of something being true or false to represent the presence or absence of something, or more specifically, to represent something being in one state or another. But what we do in here is, instead of using the true and the false, we use numbers, and the numbers are for a reason. We use numbers if something is true, or something is on, or something is there, or something is present. We use the number 1. If something is missing, a signal is not there, we use a 0. So instead of using this idea of being there or not there, off or on, false or true, what we really want to represent is something being either in one state or another state. So what we're doing here, instead of using true or, we can use anything we want, but instead of using true or false or on or off, we use a 0 or a 1. For the false condition, we use a 0. For a true condition, we use a 1. So just kind of roll with this for a second, it'll start to make sense. So each one of these numbers here, either a 0 or 1, has a special name. It's called a bit. A bit is a 0 or a 1. Now, what you can do with this is, this 0 or 1, let me get rid of this. my bits are 0 or 1. But what I really want to do is to change it into some kind of a signal, into a voltage or current. So what I can do in this system that I'm kind of just making up as I go along, if I want to, how do I represent a 1 or 0 to a machine, to an electrical machine? Machines don't understand true or false. They don't understand ones or zeros. The only thing a device, an electrical device, can understand is the absence or presence of a signal, a current or voltage. So if I want to represent inside of a digital device like your cell phone or computer, if I want to represent what I'm calling a 1, I can use any old voltage I want. If I want to represent a 0, I can use any old voltage I want to use for a 0. And it turns out what we're going to use in this class is we're going to use 5 volts to represent this 1 here and 0 volts to represent a 0. The bits right here, these numbers, these are called binary digits. And we actually get into this a lot in the class, and I think next week we talk about binary. But binary, think of binary as the mathematics of digital signals. And the simplest thing to think about in binary is the 0 and the 1. 0 and 1, the binary number system, is basically, since all of this logic stuff that we're talking about, all of this logic stuff is based on switches. And the switch can either be open or closed. So your computer, any kind of digital device, anything that contains a microprocessor is a digital device. And most devices now are digital, by the way. So the information it wants all the information that it needs to operate like this, in zeros and ones. Okay, so I don't want to stray too far away from it, so let me kind of go back over here. So here's the question I'm trying to answer. Here's what I'm trying to get you to see. I think everybody that's listening to my voice, you understand what analog is. Analog is continuous. So if I have, I mentioned temperature, or if I like pressure on the board, I can press and I can press harder, and that pressure or force goes up in a continuous way. It doesn't jump from one to the other. So most things that we measure in nature, most physical quantities are continuous. Analog. Well, that's a problem, because what we're trying to do in this class is use a computer to control processes, but computers don't work with this kind of information. You couldn't take this temperature time graph and feed it directly into a computer. It won't work. Some kind of way you got to convert this into zeros and ones. Now, the zeros and ones that I think one of you guys mentioned already, that's called machine language. Let me write that down. Machine language. Machine language. Devices, digital devices only understand zeros and ones. All I'm saying is digital devices only understand machine language. And even though we're saying zeros and ones, I'm using the term binary 0 or binary 1, really under the hood, really what I'm saying is it's going to be the presence or absence of a signal. So what I want to do is I want to take this continuous blue line here and I want to digitize it. How do I digitize it? Well, I told you to get up and you take these recordings, and so you got these data points right here. But the actual process of digitizing it means that I'm going to take this value right here, and I'm going to represent it with a series of these numbers right here, these binary numbers. So here's what happens. What you would do to change this graph from analog to digital is you say, all right, I'm going to assign this data point right here a series of zeros and ones. I'm just making this up. There's no right or wrong way to do this. I'm just making it up. So I give this right here, that data point, this series of ones and zeros. This is called a digital code. And I'll do the same thing here. I take this data point and I will assign a series of zeros and ones to this point. So maybe I assign 1, 1, 0, 0, 1 to that. And I got to do that for every point here. Every data point that I took, I got to assign a series of zeros and ones to it. I got to assign a digital code. Now remember what I said earlier. what is a 1? Well, the 1 is the presence of a certain voltage level. What is a 0? A 0 is the absence of a certain voltage level. So I can have this binary code. I can have this. Let's say I have this code right here. It's a 1, 1, 0, 1, 1. Well, inside of the computer, there is no such thing as a 1. What you really have is, whatever this position is, you got 5 volts here, you got 5 volts here, you got 0 volts here, you got 5 volts here, and you got 5 volts here. Physically, we're talking about the presence or absence of a voltage, but we abstract from that as humans. We abstract from the idea of voltage, and we assign the presence of a signal a binary 1, and the absence of a signal a 0. So that's what's really going on. So I don't want to really deal on this level. I only want to deal with 0s and 1s, these binary codes. The point is for every point right here, I'm going to have a code over here. And that right there is what I mean by digitizing. It's not just putting a dot right here and calling that a data point. It's taking that data point and representing that data point as a series of 0s or 1s. That's what I mean by digitizing. So when you digitize something, it's a process. Now I want to say a little bit more about that. I know I'm going to run out of time, but this gets kind of interesting and it gets kind of deep. Let me ask you a question. Look at this right here in the graph. Let me blow this up a little bit. So I got this point right here. I got that point right there. And these 2 points represent information. In this case, it represents temperature and time, right? I got 2 coordinates, temperature and time. So these points represent information. But what about the blue line between this point and this point? What about this? The line between these 2 points. That also represents information. And when I digitize it, basically what I do, I gave this point right here a code. I didn't do anything with the stuff in between. I gave this point right here this code of 11011. And I gave this one some other digital code. I didn't do anything with the information in between. So when you digitize it, when I turn these data points into codes, what happens to the information in between the 2 data points? What happens to it? And the answer is, you throw it away. You throw it away. Is that good or bad? Well, I mean, I don't know. It depends. It depends on how much accuracy you need. In some cases, this might be a bad situation. In other cases, it might be okay. What I mean by that is this. Let's say, remember I talked about the picture in the newspaper and the Polaroid? Let's say I want to make a line. Now, I don't know how you guys can see this in the camera. I have no idea. But let's say I want to make a line. So here's my analog line, but I want to make it digital. So when we deal with pictures, digital pictures, now we're dealing with what we call pixels. A pixel is not a 1 or a 0. A pixel is the absence of a point. Okay, so if I want to take this and digitize it, I can break it up into points like this called pixels, and I can make a line. Now, if you can see this in the camera, you can probably tell that that's not really a line. You can probably tell that that's a series of dots. Well, I can get better. I can add more dots to this. I can make the dots closer together. And in the camera, you can probably tell that still that these are a series of dots. But where I'm going with this is this. I can actually start making these dots so close together. If you're far enough from it, it looks like a line. At that point, I don't have to put them any closer together. That's good enough. If I want it to look like a line, if I'm far enough away from it, these dots actually merge into a line. I can't see the separation between the 2. So what I'm trying to say is, even though we're throwing the information away between these 2 digital codes, we're throwing the information between these 2 data points, we're throwing the information away, that might be okay depending on what you're doing. If it's not okay, what you got to do is you got to add more dots in here. In other words, if I say, look, I need a better graph, I need a more smooth graph, instead of waking up every hour, maybe you wake up every half hour and you take data points, or every quarter hour and you take data points. The more often you look at the temperature, the more dots you're going to have. We call that resolution. The more times I'm going to use the word sample, because that's the word, I don't know what other words to use, but every time you look at this, you're taking a sample of the physical quantity. And so if I can take a sample at the first hour, I take a sample at the second hour, I take a sample at the third hour, I can get a higher resolution if I look at my physical quantity more often. So instead of looking at it every hour, maybe I'm looking at it every half hour. So I look at it here, and then here, and then here, and then here. Or maybe I look at it every quarter hour. So I now have data points that are closer together. So I can sample the signal, I can take that sample and represent it with a series of zeros and ones. If I need a better, a more accurate representation of the analog signal, I just sample it more often. I increase the resolution by getting more data points. Now I only got about 6 minutes, and you might be sitting there thinking, well, man, this is kind of confusing. Why would you want to go through all of that? Why do I want to take something that's analog and digitize it? Why do I want to take something that's continuous, a signal that's continuous, and go through all this trouble of taking samples of it? Then I got to take the sample, and I got to, some kind of way, assign that sample a binary value. And now I got to take the zeros and ones. I got to put them somewhere. I got to take those zeros and ones, and I got to store it somewhere. Why would I want to go through all of that? Well, there's two things that are two important points I want to make about that. Why not take something that's analog and go through this process of digitizing it? What advantage does digital have over analog? So I'm probably going to end up with this point, talking about this point, the digital advantage. So write this down, because this will come up. There's something called the digital advantage, and I'm going to give you two on the list of several, two that's important for this class, the digital advantage. Okay, thing number one. With digital, well, let me give you an example of why you would want to do this. I don't know, you guys are so young. When I was your age, we used to record music on a cassette tape. I don't know if you know what a cassette tape is, but basically it's a piece of plastic on a little thimble that spins, so I can record music. And let's say I recorded some music on a cassette tape. I'm listening to whoever your favorite artist is. And so I have the original one that I bought from the music store. And then my buddy says, hey, Ron, I want to make a copy of that. So back in the day, we called that the dubbing the tape. I want to copy the tape. So we got a special machine, a tape machine. It has two places I can put a tape, and I can put another one, and I can transfer, or I can copy one to the other. So I can take my original tape and make a copy, and he gives me the original back, and now he takes the copy. So here's a copy of my music. Well, his friend says, hey, man, I want a copy of that. So he gives him the copy. What we're going to end up doing is making a copy of a copy of a copy of copy. The very first cassette tape I had, the one I started with, the one I bought from the store, that's called the master, the original. And every time I make a copy, if I make one copy, that's the first generation. If I make the second copy, that's the second generation. Then the third generation. Every copy is a generation away from the original. Well, it turns out that if I keep making a copy of a copy of a copy of analog signal, any kind of analog, then the quality of it degrades. Eventually, if 100 or let's say 1,000 people made a copy of that cassette, making a copy of a copy of a copy, the 1,000th person, that his music would sound, well, I can't say the word on camera, but it's a 4-letter word, begins with the S and ends with the T. The music would sound really crappy. Not so with digital, because any information, now understand what I'm about to say, please. Any information, listen, any information that goes into a computer cannot be analog. It's got to be digital. So it's got to be some kind of process whereby we take the analog information and we digitize it. We do this to it. Now think about what goes into a computer. Right now, everybody who's still here in class, you hear my voice. And there's a cord on the camera going over to the computer. You can see me, you can hear me. So I have audio information going into the computer. I got video information going into the computer. But remember, computers can't understand anything that's analog. My voice, sound is analog. The picture is analog. So some kind of way, there's circuitry in the computer that takes the analog voice information and does this to it. It takes the information and assigns it binary codes. It codes it, it digitizes it, and what goes into the computer are really zeros and ones. If I take a picture, the picture I had before, and I run this through a scanner, and I get this inside of my computer, each one of these pixels, I got a pixel that makes up this house. So here's the house in pixels. Each one of these pixels is given a binary code. And what's stored is not the picture. What's stored in any digital device is this series of binary codes. Now here's where this gets interesting, because in essence what I'm saying is anything that goes into any device with a microprocessor, any sound, picture, it doesn't matter what it is, it's all converted to zeros and ones. As a matter of fact, if you can open up and look into the microprocessor of your cell phone, your microwave, your computer, you can't tell video from audio, from a picture. Everything is just a bunch of zeros and ones. So go back to my music example. If I have a digital recording and I make a copy, what I'm copying is not some continuous signal. What I'm making a copy of are these zeros or ones. I'm making a copy of these digital codes. It's more mathematical. So this never, I can make a copy of a copy of a copy of a copy, and I'm still using the same exact digital codes that were in the original, that were in the master. And so one advantage that digital or digitizing has over keeping things analog is that digital never degrades. If I make 1,000 copies of anything digital, the nth copy and the master, the original, are exactly the same for the most part. So here's what I want you to write down, because I'm out of time now. Thing number one, the digital advantage. Advantage number one is that digital does not degrade. I can make a copy of a copy of a copy, and the nth copy, the nth generation, the nth, I'm saying n, the nth generation is exactly like the original. Digital doesn't degrade. And I'm out of time to give you the other example that I want to give you, so I'll just tell you what it is. The digital advantage. Number one, digital does not degrade. I can make a copy of a copy of a copy. And number two, I can do something to digital that I can't do to analog information. I can take digital information, I can make it smaller. That's really big. That's important. I don't have time to go into it now. But what I mean is I can take digital information, I can compress it. I can make it fit into a smaller space. Okay, so guys, I got to end with that. I want to say a little bit more about compression, but I don't have time because I got a vet appointment. I got a sick dog at home. I got a vet appointment at exactly 10:30, and my house is probably 15 minutes away from the school, so I got to run. So I can't take any questions, but if anybody has any questions over anything we talked about, I threw a lot of information out there, and I'll kind of go back to it on Friday. Hopefully I can get through everything Friday, and I'll have to spill it into Monday. But if you have any kind of questions, I'll take the questions before the next class, and then we'll do some more of this. So guys, stay safe. Have a great rest of the day, and I will see you on Friday. And again, if you have any questions, please ask me on Friday.